Okay, let's get to look at the quiz. And the first question on the quiz is determine if the following series converge conditionally, absolutely, or diverge. Be sure to state the theorems you're using. Okay, so let's look at part A. And notice, by the way, part A, part B, part C, there's no tricks or anything. They'll have a -1 to the n. So they're clearly all alternating. Is that clear to everyone? Okay, there's, again, this is the quiz on an alternating series, so you're going to see -1 to the n's. So let's take a look at this, and to decide whether it converges conditionally, absolutely, or diverges, the first thing I do is I just take a look at it, kind of ignore the -1 to the n, and see what I see. And I see an n+1 over n+2. What do you think is going to happen without doing any work?
It's going to go to 0.
n+1 over n+2?
I was thinking if you plug in.
Plug in a trillion. Okay.
Yeah, I think it goes to 1, doesn't it? Because of the
Yeah, I see a
leading
1
coefficients.
because
Yeah.
remember that it's the highest power of n that matters, and it's just n over n. So that tells us that we think this is going to diverge. Okay, it's just a thinking. We're not there yet. But that way, it gives us an idea of what should we do. Okay, so if we think it might diverge, and we look at it and the limit doesn't seem to go to 0, then let's take a look at the divergence test. So let's take a limit, and let me, I think the easiest is to, always does. There we go. So let's take, the easiest is copy and paste it in, and then play around, turn it into a limit. We're going to take a limit of the, you could do the absolute value, you might as well, but you don't have to. Okay, we could just do L'Hopital's rule on this. It's very simple. There's a limit of 1 over 1 by L'Hopital, because the numerator and denominator both go to infinity when n goes to infinity, and 1 over 1 is 1. And the important thing is that 1 where is it? Should be interrelated. There it is, not equal to 0. All right, so if we take a limit and we get a number that's not 0, what does that tell us?
Yeah,
The series diverges by what test? Yeah, by the divergence test.
Could you also use the comparison test for this one? Or
what are you comparing with?
n over n, which would also go to 1, which is also a diverging series.
Yeah, it's twice as much work.
Yeah.
I mean, you could do that, but you'd have to use a limit comparison test, right?
Yeah.
Unless you know one's bigger than the other. That's a whole lot more work. Do you agree this isn't much work the way I did it?
Yeah. I just the comparison test was more fresh in my head, so I.
Right, but the comparison test only works if you have an inequality. If you know one's less than the other or greater than the other, and it may not be obvious with this one. You could use a limit comparison test, but it's just a lot. I mean, there's no reason for that.
Yeah, I should
take a quick limit and you're done.
Divergence test.
Yeah, I mean, you definitely want to be efficient if you can. And this was not supposed to be a trick question, by the way. Okay, let's look at part B. So part B, we look at it, and if you kind of ignore the -1 to the n, what does it look like? Do you think it converges or diverges? Take a look. What do you think? Converges or diverges? If you just take an absolute value. This is supposed to be pretty easy. Yeah, this one looks like it converges. So let's consider the absolute value of this guy. Oops. Which means that we get rid of the -1 to the n. Which just becomes a 1 on the top. Okay, what test do we use for this guy? Yeah, this is a geometric series test. Okay, so by the geometric series test, note that 1/7 is less than 1 in absolute values, but maybe I'll put the absolute value just to remind you that that's supposed to go there with the geometric series test. This series, and actually this series diverges, sorry, the first one, therefore, the series, well, series diverges is fine, sorry. I was on a different track. Okay, so this series converges. But if we took an absolute value and we got it converging, because it converges absolutely. Any questions on that? Okay, and that's all there is to that. Okay, now let's look at the, so part C is the summation of -1 to the n over n minus 1.8. This time we take an absolute value. Let's do that. And let's see what happens. So if you take an absolute value, the -1 to the n goes away. That's the whole point of the absolute value. And technically, we're taking the absolute value of n minus 1.8, but we only care about large n. And as soon as n is bigger than 2, it's all positive anyway, so we don't have to worry about it. Is that okay? Okay, so you only worry about large values of n, so you can get away with ignoring the little details about the first term. All right, let's look at this series. Now, what can we say about this series in terms of what kind of test should we use?
Could you use the comparison test of 1/n?
Exactly. So use the comparison test. Comparison test with 1/n, and the summation of 1/n, maybe I'll pop it in. The summation of 1/n, does it converge or diverge?
It diverges.
Diverges by what test?
Harmonic series test.
The harmonic series test. And remember, it is an absolute requirement that you have to name the tests as you're using them. I take off points if you don't. Okay, so diverges by the harmonic series test. Okay, so did we just say this series, we're done, the series diverges? What do you
No,
think?
we also have to check the not absolute value, just using the alternating series test.
Yeah, now we need to check the alternating series test. Okay. If you use the divergence test and it diverges, you're done. Okay, that one's the automatic. Okay, because remember the alternating series test takes a limit and then it goes to infinity and checks to see whether you're 0 or not. So same thing. So now what we can do is we can take a limit as n goes to infinity of 1 over n minus 1.8. So let's adjust this. So instead of a sum, we're going to take a limit of that. And what is the limit as n goes to infinity of 1 over n minus 1.8?
0.
That's 0. Right? 1 over infinity is 0. So now what we can say therefore, by the alternating series test, the original series converges conditionally. Any questions on that? Okay, so you notice it was an ABC because I wanted to give you one of every type. Any questions at all on question 1? Okay, let's look at question 2. Consider the series summation n equals 1 to infinity, negative 1 to the n over n squared. According to the alternating series remainder theorem, what is the maximal absolute error when using the summation n equals 1 to 9? Negative 1 to the n over n squared to approximate the above series. This is actually a really easy problem if you know what to do. So what do we need to do?
Don't you just
In
find
10 for b
8
of n.
n plus 1?
Yeah, plug in 10, right? So plug in 10. Okay, and technically we got to take an absolute value because we're finding the absolute error to get. Well, we can now say the error. Let's go absolute error is less than 1 over 10 squared. Make it look prettier, actually. So the error is less than 1 over 10 squared. Which is equal to 0.01. And that's it. That was supposed to be easy if you know what to do. I even tried to make the numbers nice. Any questions at all? Any questions at all on this quiz? Any questions? Okay, if there's no questions, let's get on to our new topic. And let us go there. And what we want to do now is do something called the ratio test. So I want to remind you maybe a little overview of some of the tests we've already done. Okay, so we've already figured out that if we happen to be able to compare something with another series that we know converges or diverges, then we could figure out if our series converges or diverges. And that's great if there's something good to compare it with. Is that clear? Okay, but it could be a little messy too, and that's one thing to worry about. If it happens to be geometric series, then that's obvious, you just do it. Or P series, you just do it. Or if you can integrate easily, then you go for the integral test if it is decreasing and if it is monotonically decreasing and positive. We talked about if you have positives and negatives and they alternate, you do alternating series test. Okay, so we got all these different tests, but then there's a new test, okay? And that's called the ratio test. And it's kind of interesting with the ratio test, kind of like the comparison test, kind of like the limit comparison test, but it's comparing with itself. It's kind of weird, isn't it? And I want to think about kind of the difference between, let's say, 1 over n and 1 over 2 to the n. Both of those go to 0 when n goes to infinity, right? But 1 over n diverges, and 1 over 2 to the n converges. So what's the difference? What's going on between those two series where one converges and the other diverges?
One's arithmetic and the other's geometric.
Those are words, but what's going on with the series itself? Right, they're both going down to 0. But what's happening? What's the picture? Yeah, it has to do with how fast it goes to 0. Does that make sense? Okay, well, if you think about it, how does your car measure how fast you're going? If you've ever driven lately, no one's driving anymore, although people are starting to get back in. How does it measure how fast it's going?
Rotations.
Mm-hmm. Yeah, it does. It does rotation. So what it does is it measures, it looks at where you are now to where you are to the next rotation and divides by how long you've gone, right? And that's how you decide what your velocity is. So we're going to do basically the same thing. Is what we're going to say is we're going to not just say, does it go to 0, because that's the divergence test, and that works sometimes, but it fails most of the time. But we want to find out how fast it goes to 0. And the way you find out how fast it goes to 0 is you compare where you are now with where you are in the next rotation. Does that make sense? And the way we're going to compare is we're going to look at the ratio. So we're going to look at the ratio of where you are at the nth point to where you are at the n plus first point. And if it's going down fast, then the n plus first point divided by the nth point should be small. Whereas if it's going down not fast enough, then that ratio will be big. Any questions on kind of the idea before I state the big theorem? Okay, so here comes a big theorem. Okay, and it's a major one. Okay, so ratio test. And let's make it pretty. Uh-oh. There we go. All right. And I'm not going to write this all out, but let's suppose that we have a series. Maybe I'll write let summation of an be a series. Okay, and remember, if I don't write down the limits, just means from n equals something to infinity. Okay, so let's suppose we have a series. Then, 1, if the limit of a sub n plus 1 over a sub n is less than 1, Okay, so we're looking at the next term, and guess what? The next term just drops significantly. Okay. What do you think might happen if the next term drops significantly? And it happens every time. What do you guess?
The limit converges?
The series converges.
Series converges, sorry.
Then the series converges. 2. And the nice thing, I can copy paste and just change a couple things. If the limit is greater than 1. So now you look at the next term and it's got bigger. Then what should be true? Yeah, then the limit diverges. And the series diverges. Okay. 3. If the limit, what's left? No, 0 is less than 1. So we've already got 0.
Yeah.
So what's left?
Equals
Yeah, if
1.
it is 1. So if it's equal 1, right? You could be greater than 1, you could be less than 1, greater than 1, or equal 1. Okay. Then what we do, I wonder if they, no, I don't think it shows me that. Then it's bad. What does bad mean?
That the test doesn't work?
Yeah, then the test failed. So try another test. Don't even state that you used that test because you really didn't. You got nothing out of it. Okay. Okay, so this is a major test. I want to note something. The ratio test is especially useful when you see factorials or powers, nth powers. Okay. Well, let me do it. There it is. Okay. Just a note. How often, what percentage of the time do you think you're going to see a factorial in real world applications? And think about what we've been doing and how often you see factorials
Pretty often.
for these series. So in terms of, true applications, how often are you going to see a factorial? What do you think? What's your guess? What percent of the time?
30%.
It's a good guess. Now I'm going to tell you the weird news. It's around 90%. Okay, and again, you're not ready to know why yet, but it has to do, I'm sure you're all thinking this, but it has to do with taking n derivatives of a function. And factorials happen because each time you lose 1. So they happen a lot. Okay, so almost all the time, you're going to see factorials. The ratio test is the most important test of all tests of this whole class. Okay, but you're not going to really understand why for another week. And then it'll just be clear. And you'll say, well, of course, factorials happen all the time. And the ratio test is what you use. So that's a big note, is that the ratio test is almost always the first test you use. And it almost always works. Okay, so that's important. Okay, so again, I'm pausing here because it's so important. I want you to be looking at this ratio test and know it, because we're going to be using it a lot. All right, so now the question is, why is it true? Okay, so we look at this, and maybe I'll just focus on 1 and 2. Why does it fail? It fails because I can come up with 2 examples where the limit goes to 1 example diverges the other example. That's how you show something fails. Right? Is that anything you can come up with examples of both ways, that means it fails. Okay? On the other hand, if we look at the limit and we don't get 1, then what we can say, we can look at this, the series and 1 at a time. Well, if you take the ratio, and let's say you get, instead of 1, let's say you get, how about a third? Well, if you get a third, then each time you are decreasing by a factor of 3. Is that clear? Or you could say increasing by a factor of 1/3, same thing. So now let's think about what that really means. So if we start out with AN, let's do this in, so you have AN, and then we're going to look at the next one. The next one's AN plus 1, right? So A sub n plus 1. And then the next one is going to get boring really fast, by the way. You get A sub n plus 2. And then I'll do one more. You get A sub n plus 3. There's a reason why I'm dealing with this stuff. Oops, n plus 3. Dot, dot, dot. Well, what we can do is we can say that these guys are less, and actually maybe instead of, I'm going to let it be commas, but I'm just going to say less than. And again, if we got, let's say we take the ratio and we get, let's say we get a third for the ratio. Well, if we get a third for the ratio, then it's less than, instead of taking a third, just do a half. Okay, because a half makes it bigger, right? So what I can say is this is going to be less than A sub n and then a half A sub n. Because A sub n plus 1 is going to be bigger than a half A sub n, right? If we're thinking about kind of a third. Well, let's look at A sub n plus 2. Well, A sub n plus 2 is going to be less than a half of A sub n plus 1, which is less than a fourth of A sub n. Well, the next one, A sub n plus 3, will be less than a half of A sub n plus 2, or an eighth of A sub n. Any questions on this inequality, the sequence of inequalities? All right, so what happens now if I take the sum So now what we can do is we can take the sum of a sub n, and we can say that that is going to be less than the sum. And I'm assuming everything's positive, something to do with absolute values, by the way. Okay. In fact, in here, that was a mistake. I probably should pull some absolute values in. Or it's not quite right, because we're only looking at positive things. So I got a little bit lazy there, but I should do it. I should do it right. There we go. There we go. Okay, so here in this little kind of proof, I'm just going to assume everything's positive. Otherwise, take absolute values. And what do we see? Just want to make sure, can you still hear me?
Yeah.
I just got an error message on my computer that said, you're signing off now. So I want to make sure I'm not. I don't know what happened. It said I'm already signed in. I'm not signed in again. Okay, so what do we have? We have summation a sub n is less than, well, what happens when I add up all these other terms?
Shouldn't it be just a sub n?
Right. Well, in particular, though, now I'm going to think about, let's call it a naught instead of a n. It's going to be a naught. It's going to be 1 over 2 to the n, or 1/2 to the n. Let's write it that way. There we go. A naught. Because we can now think about this, instead of starting at the nth term, just start at the 0th term. Assume that this works for all of them. But here's the thing. You look at the right-hand side, does it converge or diverge? And how come? By what test?
P-series?
Good try. It's not a p-series.
Geometric series?
Patrick. Yeah.
Yeah, it's a geometric series. So remember the p-series, the n and the number are switched. The n's the base, the number is the exponent. Geometric series, the number is the base and the n is the exponent. Okay, so this guy converges by the geometric series test. Therefore, the original series converges by the limit comparison, by the comparison test, because we have the comparisons work. Okay, now again, I kind of gave the example if 1/3 was the ratio, but I could have used any number. I decided to make it numbers because it's easier to see. Okay, so whatever that ratio is, you can always basically take the midpoint between that ratio and 1, and then you end up with a geometric series that you're comparing with that converges, and therefore you're done. And by the way, if that less than sign was a greater than sign, then everything's exactly the same with greater than signs, and it diverges by the geometric series. That's why 1 is important. It turns out 1, there's 1 in the theorem, is because of the geometric series test, is that 1 is that boundary line at which you need to be less than 1 for the geometric series test to converge. and you need to be greater than 1 for it to diverge. And if it's equal, again, you can just come up with some examples. Trust me, sometimes it works, sometimes it doesn't. Or sometimes it converges, sometimes it doesn't, which means you can't make any conclusion. Any questions at all on this big theorem? Okay, so now we have a theorem, let's use it. Let's do some examples. Okay, so the first example is going to be a really important one. Let's look at the series. I'm just not going to put the numbers for a reason, though. So n equals 0 to infinity. Of, how about 3 to the n over n factorial. And I guess I should put the question is, just determine if the series converges or diverges. Okay, so we look at this and we need to do a test. Okay, and notice, do we have another test that'll work? Can you use the integral test? What do you think? Yeah, this is an absolute no on the integral test because there is no function, right? You can't just write, 3 to the x over x factorial, because what is x factorial if, say, x is, I don't know, 17.3? So integral test directly fails. Is that clear? Okay, this isn't a geometric series. It's not a p series. Okay, none of that works. Okay, you could try comparing, but that's going to be tough to come up with something to compare it with, because these both go up really fast. Does that make sense? So this is a tough one. Okay, none of the tests we've had will work. And by the way, why will the alternating series test definitely not work on this?
Because there's no -1 to the power of n.
Yeah, this one stays positive. You can't use an alternating series test if you don't have an alternating series. Makes no sense at all. All right, so I just wanted to go through all those because that's what you're going to be doing on the exam, is you get to decide what test to use, and you want to be able to go through each of them really quickly until you get one that seems to have potential. Is that clear? This one pretty much has to be done by the ratio test. And the nice thing is this is a beautiful one for the ratio test. So we're going to use a ratio test. So to use a ratio test, what we need to do is we need to take the limit. And again, everything's positive, so you don't have to worry about absolute values. So we'll take a limit as n goes to infinity, and I'm going to be lazy. I'm not going to write the n that goes to infinity, but hopefully you're okay with that. And I'm going to show you a shortcut. It makes it a whole lot easier. And that is, just as we do this, we realize that if you take an plus 1 over an, and they're fractions, that's the same thing as taking an plus 1 times the reciprocal of an. So that's what I'm going to do. So we have 3 to the n plus 1 over n plus 1 factorial times, it's just the reciprocal plugging in n. So n factorial over 3 to the n. Any questions so far? Okay, the next thing I'm going to do, and it's basically just so you can understand what's going on a little better. I'm going to write equal, and I'm just going to do a little easy math switch. I'm going to put 3 to the end first. That's not what I meant to do, but it'll work anyway. It's just being messed with me. Just a minute. Let's try this again. And then I'm going to put the n plus 1 factorial last. So it's going to kind of switch around. And this is a big suggestion I have for you. When you're doing the algebra, when you're using the ratio test, put like stuff with like stuff, and life will be a lot easier for you. Because now we can do some very simple simplification. And what we can say now is we can say, what is 3 to the n plus 1 over 3 to the n? And the hint is it's very nice.
3 to the n.
It's not 3 to the n. It's even nicer.
1/3. Wait. Oh.
I like what Jesus says. It's 3 to the 1, but even nicer than that, it's 3. Right? Rule of exponents says you subtract. What's n plus 1 minus n? I hope that one you can do in your head. N plus 1 minus n is 1, right?
Yeah.
So 3 to the 1 is just 3. I'm going to write as a fraction now. Now, what is n factorial over n plus 1 factorial? That's actually pretty nice too. Not quite as nice as 3, but it's actually very nice. I don't see y'all jumping in. Let's think about, say, 5 factorial over 6 factorial. Well, that's 5 times 4 times 3 times 2 divided by 6 times 5 times 4 times 3 times 2. And you get a whole lot of canceling. What are you left with? Yeah, 1 over n plus 1. And that's why, by the way, the ratio test works so well for factorials, because factorials wonderfully simplify when you divide n factorial divided by n plus 1 factorial. Any questions at all on the algebra that just happened? Okay, now as always, algebra is hard, calculus is easy. So what is the limit? Now let's do the calculus. As n goes to infinity of 3 over n plus 1.
0.
That's 0. And the important thing about 0 is definitely less than 1. You better all know that. So what's the conclusion? By the ratio test.
It converges.
Yeah, our series converges. And that's it. Any questions at all on this example? Okay, by the way, am I ever going to ask you what it converges to?
Oh, hopefully.
The answer is yes,
Oh.
but not today. Remember, we have a whole nother chapter. So I know you're all thinking this because you all knew, but that it converges to e cubed. Right, you're all thinking that, right? Okay, so this actually converges to e cubed, e to the 3rd power. Okay, and by the end of the quarter, you'll be able to look at that and know just by looking, but not today, that this is actually a really important series. Okay, there's a generalization that's really important. Any questions at all on using the ratio test for this example? Any questions? Does the ratio test always work?
No.
No, no. When does it not work?
When it equals 1.
When it equals 1, yeah.
Yeah, there's 2 times when it doesn't work. One is when you get 1 for the limit, and then the test just fails by theorem. When else does it not work?
I was thinking when, like, you know how we have 3 over n plus 1? Maybe if there's a situation where we get 0 in the denominator.
No, then you get infinity if everything's positive, and that's greater than 1. So that worked. Should I tell you?
Yeah.
Okay. The other time it doesn't work is when you can't figure out how to take the limit. Not all limits are nice, right? There are examples where you look at that limit and you have no idea what to do. You've probably been there in first quarter calculus, right? So that's just a note, is that the 2 times ratio test doesn't work. Is one is if you get 1 for the limit, and the other is if you can't figure out the limit. Okay. All right, what about, let's do one that we already know the answer to. As I've mentioned a bunch of times, what's the most famous theorem? Most famous series?
Harmonic series?
Harmonic.
Yeah, let's do harmonic. Whoops. Try that again. And will the ratio test work on this? What do we have to do?
Set up our limit.
Yep, we set up our limit. We take a limit, and now we're going to have a ratio, and it's going to be 1 over n plus 1 times n, or n over n plus 1. Everyone okay with that? And what do you get?
0.
You sure?
No,
1.
We get 1, right? Because you get infinity over infinity, and then you can use L'Hopital's rule. You get 1 over 1, which is 1. What's the conclusion?
Failure.
Yeah. So the conclusion is use another test.
Probably the one that it's named for.
Yeah, I mean, right. And we did that one because we proved it. Okay, but if you want to prove it, you can use, we did the proof just in general. You could also use the integral test too. But the ratio test fails miserably. Okay. By the way, do you think you could use a comparison test?
I mean, don't we usually use this as in the comparison test?
Right, so the
Yeah.
answer is no. Yeah, this is like the standard comparison thing to compare with. Good luck finding something else. Yeah, so basically the test, you use a harmonic series test, which we know that is a harmonic series. Okay, but I wanted to show you an example where it just doesn't work. And this is such an easy one, I figured that I could quickly. Any questions on this test?
I'm just curious as to how you set up as n over n plus 1, the algebra behind it.
Oh, okay. So let's do that. So we have the limit of 1 over n plus 1. do that. So we have a 1 over n plus 1 divided by 1 over n, which is the same as multiplying by n over 1. Does that make sense?
Yes.
Yeah. So sorry if I did a piece in my head that was too much to do in my head, but that was a piece I did in my head. Okay, and by the way, with the ratio test, just about every time you're really thinking about plug in n plus 1 and then take times the reciprocal of what you started with. That's almost always the case for ratio test.
Okay.
Okay. Any other questions? Okay. Now comes the last test. And this is called the root test. Okay. And by the way, something that I've never liked, but we can't do anything about it, is notice I'm not using abbreviations for the tests when I say by the ratio test. Do you see why?
Yes.
There's the one, yeah, unfortunately, ratio test and root test, if you abbreviate, then they're both RT. So this is the one case where I actually use the whole word. Fortunately, the words are pretty short, so it's not too hard to write it out. So it's called the root test. And it's kind of what it sounds like. Hopefully, you know what it means. It does not mean we're going to go to a tree root, by the way. And what it says is the following. I'm going to just kind of copy the ratio test because it starts the same. Okay, let A and be a series. Okay, then if, okay, now it's a different limit though. If the limit of the, let's see if it'll allow me to do this. Yep, good. Nth root of A sub n is less than 1, the series converges. Okay, and if the nth root of A sub n is greater than 1, the series diverges. And as you might guess, if the nth root of A sub n equals 1, then the test fails, so try another test. So that you can see why they call it the root test, because what we're doing is we're taking the nth root of the A sub n, the nth term, and we're seeing whether you're less than 1, greater than 1, or equal to 1. When do you think this is going to be useful?
Maybe when something fails the ratio test?
Well, that could, I mean, it could be useful, but usually not. When there's roots, good try. There's a hint. What do roots cancel?
Powers.
Powers. Okay, so here's when you use it. Okay, it's obvious as soon as you think about it. So use the root test when A sub n is of the form something and put star. Star means whatever you feel like, whatever you know, doesn't matter, to the nth power. Because if you take the nth root of that, the n's cancel. Okay, so that's the whole point of the nth root test, is it allows us to undo powers. Any questions on that? If you don't have an nth power, don't do the nth root test, because those limits are horrible. But if you have an nth power, it usually, but not always, but usually works. Okay, so let's look at an example. Okay, and by the way, this is one I'm not going to prove, because this one's way messy. Okay, there is a proof, but it's not something that I don't think is worth it for a first-year calculus class. But maybe someday, if you decide to be a math major, you'll get to play around with the proof. And as you might guess, there's epsilon delta in it. Okay, so no proofs are going to happen for this class in this particular test. But examples in the hand, those should happen. Okay, determine if the summation of two n plus 3 over 4n plus 5. To the nth power converges. Okay, so we look at this, and what test do you think is going to be best for this particular example?
You get the limit of 2n plus 3.
Right, but what test should we use?
Oh, sorry, root test, yeah.
Good, we should use a root test. Okay, and I know it's obvious because I'm just saying example of root test, but that's not going to work on your exam.
Yeah, you have to state what test you're using.
Exam, I'm just going to say determine if the following series converge or diverge, and you have to look at it, and you're going to say, well, what's going on in this particular one? Okay, this is definitely not geometric series. It's definitely not P series, right? Those are the easy ones, right? But I do see an nth power. So I notice that we have an an is something to the nth power. Do you see that? And then you can cross your fingers and hope this works. Okay, then we see that if it's an nth power, let's try the root test. If you don't see an nth power or something real close to an nth power, then forget it. So let's go ahead and let's do the limit. And what we're going to do is we're going to take this limit and we're going to take the nth root of the nth power of this fraction. Well, that's the whole point of this, is the nth root of the nth power goes away. And you get 2n plus 3 over 4n plus 5. Okay, and that we can use L'Hopital's if we want. And what's the derivative of 2n plus 3?
2.
2. And the derivative of 4n plus 5?
4.
4. And all of a sudden the limit is really easy. What is our limit?
2/4 or 1/2.
Yeah, 0.5, just because it's easier to type. And what's the important thing about the number 0.5?
It's less than 1.
Yeah, this is less than 1. And because it's less than 1, therefore, by the root test, these series summation of 2n plus 3 over 4n plus 5 to the n converges. Any questions? Any questions at all about this using the root test? Any questions? Okay, what if we had, let's do a different one. But it won't be that much different. What if we had 3n plus 1 over 2n plus 6 let's make it n plus 6, but not n power, 2n power. All right. What test do you think will be best for this one?
Root test.
Yeah, we can still use a root test. And the reason why this one will work is there's rules of exponents. So the first thing I'm going to do is I'm just going to rewrite this series as this guy squared to the nth power. Any questions on what I just did? Okay, and that's a rule of exponent, is that if you have something squared to the nth power, that's the same thing as a something to the 2n. Then we can go ahead and we can take the limit. But as you're noticing, there's going to be some algebra. So I'm going to take the limit. And we're going to have 3n plus 1 over n plus 6. Oops. Try that again. Squared. Because we took the nth root of an nth power and those n's canceled. Well, how do we do this limit?
We should probably square it first.
You mean square it all out?
Yeah.
You could do that. That sounds like a pain in the butt, doesn't it?
Yeah.
Instead, we could use the theorem that says the limit of a function is the function of the limit. Do you remember that? So what we can do is we can pull the squared outside the limit, take the limit, and then square it. And what do you get? So what's just the limit of 3n plus 1 over n plus 6? Or maybe if we want, here, let's do this so it feels better for y'all. That won't let me, so I'll do it this way. So what we can do now is we can pull the parentheses out, basically. So we take the limit of 3n plus 1 over n plus 6 squared. That was a little theorem you had in first quarter calculus that you're allowed to do that. And now this limit is easy. Can you do L'Hopital's rule in your head or not? Or do you need to see the steps?
Yeah, it's 3 squared, and
Yep.
then so it's 9. Yeah.
Yeah, so it's just 3 squared. Which is equal to 9. What's important about 9?
It's greater than 1.
It's greater than 1.
It's greater
So
than
it
1.
diverges.
Yeah, therefore the series diverges. By the root test. Any questions on this example of showing one that diverges? What do you think the hardest part is going to be of this whole chapter?
Setting up our limits.
The chapter.
Oh.
That's a hint, because not even always going to have a limit.
Being able to recognize what test you need to use based
Exactly. Exactly. So
And which one's the most efficient too?
yeah, and that's why I said by need. Because if it takes you 3 hours to do the test, that's not okay on an exam, right? So you need to be able to choose the best test to use, the most efficient. So what I thought I'd do now is go over kind of how to tell what test to use. Kind of a summary of the whole chapter. Okay, so the first thing you want to do is look for what kind of problem this is. So can you quickly see one of the following? Again, I recommend doing it in your head. Don't write it out, because otherwise it'll take too long. So just do a bunch of things in your head really fast. Okay, if you can't do it fast, then it may not be the best anyway. Okay, one is, does the limit not go to 0? Maybe I should even say, does limit go to 0? And if not, use what test? If you look at AN and you say the limit doesn't go to 0, just by looking at it because it's obvious, what test are you going to use?
Divergence test?
Yeah.
Okay.
Okay, that's a good, and again, it's not like this is the first thing you do. You look at it and decide what to do. Another one is it simple? And simple means A. That won't let me do that. Oh, I know. How about this? That worked. A. I don't think we need to make it big, otherwise we'll run out of room on the screen. So A is it of the form, actually just is it, not even of the form, is it exactly some number R to the N? If so, then what test?
P-series? No, geometric.
Geometric series test. Okay, is it, instead of r to the n, is it n to the r?
That's P-series test, right?
Yep, that one's p-series test. Okay, and r is not usually the letter you use. Negative p is usually the letter you use, so you can call it p-series test. But the letter doesn't matter. Oops, that should be a period, should be a question mark. And if so, use the p-series test. Any questions on that? Okay, so sometimes it's really quick and it's just a p-series test. Okay, and by the way, starting Wednesday, we're going to have something where you're going to have to look at it and say, depending on the value of x, you're going to have a different test to use. So we'll get there, but that's Wednesday, and I figure I'm going to wait till Wednesday to show you that. But just let you know, even in one problem, there could be multiple tests to use because it depends on x. So just trust me on that one. Okay, so that's if it's really simple. Okay, another thing you could say is, does it look like a geometric series, like GS, or a p-series? Okay, does it look like it, but it isn't one? Then what do we use?
We could use what we just learned, root and
Remember, those are special types. Yeah, we use a comparison test. So, and that is if the inequality is correct, use the comparison test. If not, use the limit comparison test. Any questions on that? Okay, and when I say does it look like it, like is there like a dominant term in the numerator and the denominator, and we just look at the dominator terms only, then it's going to be a p-series or geometric series. That's what I mean by does it look like it. Okay, then is there a -1 to the n?
Alternating
If
series
so,
test.
yeah, use the alternating series test. Any questions on that? And remember, when you use the alternating series test, you're also using other tests. Okay, because you have to decide if it converges absolutely or conditionally. And to check for absolutely, then you're going to have to use one of the other tests. Okay. I guess there should be a C on this. Is it 1 over n? If so, use what test?
harmonic series.
Yeah. Okay, next is there a factorial? And or an nth power along with other stuff? If so, what test?
Root test? I think my Zoom might be crashed. Does Larry's feed look frozen to anybody else? Or
Yeah, I think Larry's just frozen.
Yeah.
okay.
There he goes.
Bye, Larry.
Why am I in charge of like the recording now? What's going on?
Should we? I think he crashed. Should we try to rejoin the group, like off of Canvas, or?
Is class over? Like, over then?
Well, I mean, the time is he has office hours.
I'm just debating on whether or not I should stop the recording then, because
You probably should.
Yeah, I'd say it's safe to stop it.